Hello student, welcome to EPG Pathsala. I am Anshul Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to discuss about the module titled Basic Properties of Nanomaterials 1 from the paper Nanoscience and Technology 2. After studying this module, you should able to understand the following points: periodicity and crystallinity, two-dimensional Brevis lattice and FCC structure, energy band gap and classification of solid based on it, and reciprocal space and lattices. In the recent years, nanotechnology has become one of the most important and exciting forefront field in physics, chemistry, engineering and biology. The prefix nano in the word nanotechnology means a billionth 10 to the power minus 9. Nanotechnology deals with various structures of matters having dimension of the order of billionth of a meter. It is not clear when humans first began to take advantages of nano-sized material. It is known that in the 4th century AD, Roman glassmakers were fabricating glasses containing nano-sized metals. The potential importance of the cluster was recognized by the Irish-born chemist Robert Boyle in his Skeptical Chemist published in 1661. Photography is an advanced and mature technology developed in the 18th and 19th century, which depends on the production of silver nanoparticle sensitive to light. Richard Feynman was awarded the Nobel Prize in Physics in 1965 for his contribution towards quantum electrodynamics. Feynman in 1960 presented a visionary and prophetic lecture at the meeting of American Physical Society entitled "There is a Plenty of Room at the Bottom," where he speculated on the possibility and potential of nano-sized material. I want to discuss the crystal structure and periodicity. As you know, in physics, a state of matter exists in one of the distinct forms. 4 states of matters are observed everywhere in life. For example, solid, liquid, gas and plasma. In a solid, the particles, it may be ions, atoms or molecules, are closely packed together. The forces between particles are strong so that the particle cannot move freely but can only vibrate. As a result, the solid has a stable, definite shape and a definite volume. Solid can only change their shape by force, as when broken or cut. Solid can be characterized into 2 parts. It may be crystalline or amorphous. In crystalline solid, the particles, for example atoms, molecules or ions, are packed in a regularly ordered, repeating pattern. There are various different crystal structures, and the same substance can have more than one structure. For example, iron has a body-centered cubic structure at temperature below 912 degrees Celsius, and a face-centered cubic structure between 912 and 1394 degrees Celsius. Glasses and other non-crystalline amorphous solid without long-range order are not thermal equilibrium ground state. Therefore, they are described as non-classical state of matter. In geometry and crystallography, a Bravais lattice studied by Auguste Bravais in 1850 is an infinite array of discrete points in three-dimensional space generated by a set of discrete translation operations and described by R is equal to N1A1 plus N2A2 plus N3A3, where Ni are any integers and Ai are known as primitive vectors which lie in different directions and span the lattice. For any choice of position vector R, the lattice looks exactly the same. The number of Bravais lattice in 2 dimensions is 5 and in 3 dimensions they are 14 in number. Where is given in figure, we have shown the 5 two-dimensional Bravais lattice. In 3-dimensional crystal, unit cell of 14 Bravais lattice ranges from triclinic, which is most unsymmetrical, to a cubic system, which is most symmetrical one. The cubic structure have 3 forms: simple cubic, body-centered cubic, and face-centered cubic, named as SC, BCC, and FCC respectively. Among these 3, the face-centered cubic structure is most favored by the solid as a occupancy of the space unit cell. In this case is maximum, which is around 74%. Generally, there are 2 types of closed pack structure where maximum volume of unit cell is occupied by the atoms. Are hexagonal closed pack structure, which is called HCP, and face-centered cubic structure, which is called FCC. In hexagonal closed pack structure, the third layer has the same arrangement of sphere as the first layer and covers all the tetrahedral holes. Since the structure repeats itself after every 2 layers, the stacking for HCP may be described as AB, AB, AB. The atoms in a hexagonal closed pack structure efficiently occupied 74% of space while 26% space is empty. The arrangement in a cubic closed packing FCC efficiently filled up to 74% of space, similar to hexagonal closed packing. The second layer of spheres is placed onto of half of the depressions of the first layer. The third layer is completely different than that first 2 layers and is stacked in a depression of second layer, thus covering all the octahedral holes in this case. The sphere in the third layer are not in line with those in first layer, and the structure does not repeat until a 4th layer is added, and therefore the 4th layer is the same as the first layer, so the arrangement of the layer is ABC, ABC, ABC kind. The face-centered cubic structure has atoms located at each of the corners of the center of all the cubic faces, which is clearly shown in the figure. Each of the corner atom is the corner of another cube So the corner atoms are shared among 8 unit cells, which is clearly visible. Additionally, each of its 6 face-centered atom is shared with an adjacent atom, which is also very clear at their faces. Since 12 of its atoms are shared, it is said to have a coordination number of 12. The FCC unit cell consists of a net total of 4 atoms, 8 eighths from corners atoms and 6 halves of face atoms as shown in the middle image here. In the FCC structure and the HCP structure, the atoms can pack closer together than they can in the BCC or other structures. The atoms from one layer nest themselves in the empty space between the atoms of the adjacent layer. To picture packing arrangement, imagine a box filled with a layer of balls that are aligned in the column and rows. When a few additional balls are tossed in the box, they will not balance directly on top of the balls in the first layer, but instead will come to the rest at the pocket created between 4 balls of the bottom layer. As more balls are added, they will pack together to fill up all the pockets. The packing factor, which is the volume of the atoms in cell per the total volume of the cell, is 0.74 for FCC crystal. Some of the metals that have the FCC structure includes aluminium, copper, gold, iridium, lead, nickel, platinum and silver. If these are n numbers of layers, then the total number of atoms will be given by the formula here. N is equal to 1 by 3 in bracket 10n cube minus 15n square plus 11n minus 3. And the number of atoms on the surface will be n surface is equal to 10n square minus 20n plus 12. Let us discuss the energy bands. Energy bands consisting of a large number of closely spaced energy levels exist in a crystalline material. The bands can be thought of as collection of individual energy levels of electrons surrounding each atom. The wave function of individual electrons, however, overlap with those of electrons confined to neighboring atoms. The Pauli exclusion principle does not allow the electron energy level to be the same, so that one obtains a set of closely spaced energy levels, forming an energy band. The energy band model is crucial to any detailed treatment of semiconductor devices. It provides the framework needed to understand the concept of an energy band gap and that of conduction in an almost filled band as described by the empty states. The energy band formed due to the overlapping of the filled energy levels are referred as valence band, and the band which are formed due to the overlapping of empty energy levels called conduction bands. Electron present inside the valence band are tightly bound with the crystal lattice and hence are not free to move, while electrons present in the conduction band are relatively free and responsible for the conduction. At energy level called Fermi level, it defines as a maximum amount of energy up to which the electrons are filled. In case of pristine material, generally it lies in the mid of conduction and valence band. Energy gap between the top of the valence band and the bottom of conduction band is called energy band gap, defined as Eg. I give the classification of solid based on energy band gap. Based on the band structure, solid materials are characterized in three parts: metal conductors, semiconductors, and insulator. If the band gap is of order of 0 electron volt, the materials are called metal. If the energy band gap is of the order of 1 electron volt, then the materials are called semiconductor, and insulator have the band gap greater than 3 electron volts. So, a semiconductor have the finite amount of energy gap, which we have discussed just now. This band gap in semiconductors are also of two types. The one is the direct band gap and the second is the indirect band gap. Indirect band gap, which is visible in the figure, semiconductor, the top of the valence band and the bottom of conduction band occur at the same value of momentum. In an indirect band gap semiconductor, the maximum energy of the valence band occurs at a different value of momentum to the minimum in the conduction band energy. A photon of energy Eg, where Eg is the band gap, can produce an electron hole pair in a direct band gap semiconductor quite easily, because the electron does not need to be given very much momentum. However, an electron must also undergo a significant change in its momentum for a photon of energy Eg to produce an electron hole pair in an indirect band gap semiconductor. This is possible, but it requires such an electron to interact not only with the photon to gain energy, but also with a lattice vibration called a phonon in order to either gain or lose momentum. In indirect process proceeds at a much slower rate, as it requires three entities to intersect in order to proceed: an electron, a photon, and a phonon. This is analogous to chemical reaction, where in a particular reaction step, a reaction between two molecules will proceed at a much greater rate than a process which involves three molecules. The same principle applied to recombination of electron and hole to produce photons. The recombination process is much more efficient for a direct band gap semiconductor than for an indirect band gap semiconductor, where the process must be mediated by a phonon. A result of such consideration, gallium arsenide and other direct band semiconductors are used to make optical devices such as LED and semiconductor lasers, whereas silicon, which is an indirect band gap material, is not. The tuning of band gap of a semiconductor by doping. Band gap of a semiconductor can be tuned by using a process called doping. Doping means the addition of impurity into a semiconductor crystal to the definite modification of conductivity. Two of the most important materials silicon can be doped with are boron with valency 3 and phosphorus with valency 5. Other materials are aluminum, indium, and arsenic, antimony, etc. The dopant is integrated into the lattice structure of the semiconductor crystal, which is shown in figure. The number of outer electrons define the type of doping. Electrons with 3 valence electrons are used for p-type of doping, 5 values element for n-doping. The conductivity of a deliberately contaminated silicon crystal can be increased by the factor of 10 to the power 6. Let us discuss n type of doping. The 5-valent dopant has an outer electron more than the silicon atom. 4 outer electrons combined with the ever one silicon atom, while the 5th electron is free to move and serve as a charge carrier. This free electron requires much less energy to be lifted from valence band into a conduction band than the electrons which cause the intrinsic conductivity of silicon. The dopant which emits an electron is known as an electron donor. The dopants are positively charged by the loss of negative charge carrier and are built into the lattice. Only the negative electrons can move. Doped semimetals whose conductivity is based on free negative electrons are n-type are n-doped. Due to the higher number of free electrons, those are also named as majority charge carrier. Mobile holes are named as minority charge carriers, which is clear in the figure shown here. Now let us talk about p-type of doping. In contrast to the free electron, due to the doping with phosphorus, the 3-valent dopant effect is exactly the opposite. The 3-valent dopant can catch an additional outer electron, thus leaving a hole in the valence band of silicon atom. Therefore, the electron in the valence band becomes mobile. The hole moves in the opposite direction to the movement of the electron. The necessary energy to lift an electron into the energy level of indium as a dopant is only 1% of the energy which is needed to raise a valence electron of silicon into the conduction band. Due to the positive hole, these semiconductors are called p-conductive or p-doped. Analog to the n-doped semiconductors, the holes are the majority charge carriers, free electrons are the minority charge carriers. Changes in the band structure of the semiconductor can be discussed here. By the introduction of the dopant with 5 outer electrons in the n-doped semiconductors, there is an electron in the crystal which is not bound and therefore can be moved with relatively little energy into the conduction band. Thus, in an n-doped semiconductor, the donator energy level is close to the conduction band edge. The band gap is overcome is very small. Production of 3-valent dopants in the semiconductor, a hole is available which may be already occupied at low energy by an electron from the valence band of the silicon. For p-doped semiconductor, the accepted energy level is close to the valence band, which is clearly shown in the figure. Let us discuss the reciprocal lattice. The plane or the fundamental concept in the discussion of a crystal. In fact, the crystal can be specified in terms of just its lattice planes and the distances between them, instead of in terms of all of its elementary sites or equivalently its primitive vectors. Connected to these idea is the notion of the reciprocal lattice. As the name implies, the reciprocal lattice is indeed a lattice and it can be specified by its own set of primitive vectors. The significance of the reciprocal lattice is that each of the vectors is defined by joining any site on the lattice of another on it, correspond to a plane in the origin or direct lattice. Each reciprocal vector is a normal to the direct lattice plane. Moreover, the distance between the direct lattice planes will correspond to the size of the reciprocal lattice vector. The larger the magnitude of the vector, the smaller the distance between the corresponding planes. It is also worth noting that the reciprocal lattice of reciprocal lattice is the original direct lattice. Reciprocal lattice are the Fourier transform of direct lattices. The reciprocal space lattice is a set of imaginary points constructed in such a way that the direction of a vector from one point to the another coincide with the direction of a normal to the real space planes. The separation of those points, absolute value of the vector, is equal to the reciprocal of the interplanar distance, the real interplanar distance. Now let us discuss the reciprocal vector. If a1, a2 and a3 are the primitive vector which I have discussed for the direct lattice, the reciprocal lattice is described by corresponding primitive vector b1, b2 and b3 with the relation b1 equal to 2 pi a2 cross a3 by volume v, which is a1 dot a2 cross a3, and similarly b2 and b3, which correspond to bi dot aj is equal to 2 pi sigma ij, where sigma ij is the Kronecker delta. If b1, b2 and b3 represents the reciprocal lattice vector for three-dimensional Bravais lattice, the reciprocal translation vector is given by Gm, which is M1 b1 plus M2 b2 plus M3 b3. Reciprocal lattice or space vectors, lattice vector is important because energy in reciprocal lattice calculation is easier. So let us discuss energy in reciprocal space. The calculation of energy in momentum space, which is the reciprocal space, is easy. For example, let us consider the case of free particle. For a free particle, the value of potential V is 0 and hence the Schrodinger equation can be written as minus h cut square by 2m d2 psi by dx square is equal to E psi, where energy E is h cut square by 2m k square. After solving the above equation, we have an energy and the momentum of a free particle will have the value P is equal to h cross by 2m k, and the kinetic energy is given by E is equal to half mv square equal to P square by 2m, which is h by 2 pi square k square by 2m. So student, let us summarize what we have learned in this module. We have learned that solid exists in two forms, crystalline and amorphous. Crystalline have long-range ordering of atoms, while amorphous possesses short-range ordering. Two-dimensional crystal have 5 types of Bravais lattice and three-dimensional crystal have 14 Bravais lattices. Generally, metals and noble gas crystal possesses face-centered cubic structure. Similar to face-centered cubic, another closed pack structure is hexagonal closed packing known as HCP. Layered stacking in FCC is ABC ABC and in HCP it is AB AB. In FCC, for n layer number of atom is given by n is equal to 1 by 3 10 n cube minus 15n square plus 11n minus 3, and the number of atoms on the surface is given by the equation n surface is equal to 10n square minus 20n plus 12. We have also learned that solid can be characterized into insulators, semiconductors and metals based on band gap. Band gap of a semiconductor material can be tuned by doping. If A1, A2 and A3 are the primitive vector of a direct lattice, the reciprocal lattice is described by the corresponding primitive vector, which is known as B1, B2, B3, and the expression for B1 is 2 pi A2 into A3 by A1 dot A2 cross A3. Similarly, B2 is equal to 2 pi A3 cross A1 by A1 dot A2 cross A3, and B3 is equal to 2 pi A1 cross A2 divided by A1 dot A2 cross A3, and Bi plus Az is equal to 2 pi sigma Ij, where sigma Ij is the Noether delta function. Energy for a free particle in reciprocal space is given by E is equal to h cut square by 2m k square in momentum space. Thank you very much.